All right, so next part is this guy, and it's going to be challenging because he's got V's. I don't know if you can see it here. Here's a side profile up here, but he's got V's going all the way to shoulders, which, you know, to get an ideal V with a square end is impossible. So there has to be some radius, so he's allowed me some radius. But to get this small little feature up here, this V, which is the slightly smaller V here, that is going to be particularly challenging because up against this flat here, up against this vertical surface, he has got a spec 60 thousandths radius max, which is smaller than a 0.125 end mill. So we're going to have to go smaller than that if I have one. Maybe a ball end mill and try and get in there and see if we can clean that up. I don't know. That's going to be really challenging. So we've got the part here, and I've pre-dimensioned the steps in it for you because that's just very generic. But I am going to put some layout lines of where the V's are going to go here, just so I have some reference points when I'm milling this out. Alrighty, so in order to do the 45 slot in here, I've got some V blocks sitting on some A2 tool steel that's hardened ground, and I'm just grabbing the bottom of the part just below the line of the bottom cut line. And in order to have a reference point, which becomes much more difficult when you're at 45 degrees, I've done something that if you need extreme accuracy is not a very good idea. So this is the part right here, and I want the V. So what I'm going to do is I'm going to turn the part like this, so that this is horizontal and this part will be vertical, and I can plunge straight down with my end mill and cut across. So what I did is I remodeled this guy in CAD, and I took the part, rotated it 45 in CAD, and then I have a datum point here, as long as I don't care about extreme precision, right on this edge and right on this edge. And to show you what I mean by inaccuracy, so since these had to be deburred, they need to come to a perfect 90, but they don't because I deburred them. I did very lightly, but still takes off some material. So as a double check, I put the overall distance between here and here, even though this, I want this as my datum point. And it turns out that this distance is 1.587, 4 thousandths under, which makes sense. So I took about 2 thousandths off these corners. So remember, if you need extreme precision, you cannot, and I repeat, you cannot use these edges as a reference point. What you need to do instead is have like something on the center line, a ball, a tooling ball, and put it in there and use that as your reference point. I'll show you what one of those is. Here are two examples of tooling balls. This is an 1/8 inch shaft, and I think there's a 1/4 inch shaft. A 1/4 inch ball, and I'm guessing a 1/2 inch ball here. This one has no shoulder. So this tooling ball, you put it in a very carefully reamed hole, and the shoulder forces the center of the ball to be exactly 200 thousandths above the surface. This guy could be anywhere. But what it will do is no matter which direction you come from, you are always equidistant from the center line of the ball going down this shaft. So you can use that as a reference point. If you want more advice on that, I am by no means an expert. I have very limited use of this sort of tooling. I would recommend to go over to Joe Piesinski's website, and he shows a couple of really good examples of where he uses tooling balls. So back to the part. Since my reference points are about 4 thousandths under total, 2 thousandths each side, I'm going to shift it off 2 thousandths. And the reason I can get away with this is because positioning on the V block is plus or minus 10 thousandths, 5 thousandths, I'm sorry, plus or minus 5 thousandths. I'm sorry, plus or minus 10 thousandths for the edges. The center they want sort of right on with plus or minus 5 thousandths. I should be within 1,000th or so. So that'll be plenty good for this particular part. So it's a good thing to always keep in mind, which I don't, is that you want to keep your tolerances of the actual part in mind when you're doing your setup and everything, because if you're trying to do this for money, which I am charging for this, but it's mostly for my learning experience here, is that you want to make sure that you don't get too tight a tolerance because you can spend a lot more time. So in this case, it's pretty easy. I just go between these two edge points, but a whole different ball of wax if I need to be dead on. So just thought I'd bring that point up to you. It's pretty important. One more thing to point out, and I always recommend a sanity check, which is why I measured from here to here and compared it to what CAD said it should be, which you don't need CAD. You could do it with trigonometry, but CAD's a heck of a lot faster. But when I first did this, I thought, oh, I'll just reference off this bottom line. It's in line with these other two parts. But in space, it's not, because these sit higher. This part right here sits higher than this does. And when I modeled it, I based the distance off this corner and this corner. So when I measured from here to here, I was like 40,000th off. And I go, holy cow, did I make a problem with my drawing? Did I have a problem with my drawing? Turns out I did not. I needed to come off of here because this sticks out differently in space. And so be very careful to reference these particular points in space that you actually need to. Lesson learned. All right, so our first cut, we're going to try 200 thousandths depth of cut because we're just taking a little triangular section out. I don't think that should be too much. I set my Z0 by using this reference here with the 21 thousandths thick feeler gauge. Got it till I could just slide it under where it just started to scratch, and then compensate for the 21 thousandths. That's put me at 0. Then I came down the 0.318, which is my 0 along the side of this. Hopefully we'll be right on and we won't screw this up. And I purposely left some extra material on the side for a finish pass. So rather than go over 38 thousandths, I went in 50 thousandths to compensate for the 250 thousandths radius of this, because this is only 0.212, so it should be 38 thousandths under, but I went 50 thousandths under, so I left myself a little bit of material to fix at the end. I'm going to vacuum this, so I will bring you back when I'm done, because this is going to get loud. Another 100,000. So next up, I'm going to go my final dimension in the X direction, minus 32, and we're going to do a pass. Then we'll change our depth and do the final depth pass. Looks like we're right on the line, which is excellent. Here, let me show you. So you can see that the new cut point is right on the line, just to make sure those layout lines have saved my bacon on this project, because I would have totally screwed up in several cases. So I'm very pleased I did it. Final pass on the bottom. So even after I clean this up and I flip it, so what I'm going to do is I'm going to take the part and I'm going to flip it 45 the other direction so that I can clean up this corner right here, but I never will be able to get all the way in there. That is going to be a serious problem. I don't know what I'm going to do about that, because the radius of the end mill, I mean, I can go to smaller and smaller end mills, which will make this artifact less and less, but it won't make it go away altogether no matter what I do. So the goal is to get it within tolerance of what he's looking for, but how do you get a really small end mill over into the corner? That'll be interesting. All right, I've set up my dimensions for this top pocket, which is a V-groove, and it's going to be really tough to get in there. So I'm going to use an 1/8 inch end mill for starters. I might have to go smaller to get the radius he wants. And what I've got here is a solid carbide end mill extension holder, and it's 10 millimeter and has two tiny little set screws. And there's a question for someone: how the heck do they take and put threads in carbide? That's got to be a trick. It's got two tiny little set screws that hold the end mill in place. Anyways, pretty interesting. Now we're going to repeat the same operation with a much smaller end mill, and it's going to be pretty challenging, I think. I'm going to start with 120 thousandths, give myself a little bit of fix-it space later. So let's try 50 thousandths. So here's my progress with this very small drill bit. It's taking a ton of passes to remove this material. So I'm going to keep going. I'll bring you back, because not only I'll only go down 25 thousandths, I can only go in about 25 thousandths, 30 thousandths a pass, or it's risking breaking the end mill. So I probably should have started with a large end mill and then cleaned up with a smaller one, but I've already started this, so I'm going to try and finish it this way. It's not a large area. After a bunch of passes, we're getting closer. We're going to do the final depth and width and do the back and see how close we can get. Small bites. Now we're going to walk the back in. We're going to take the x-axis this way so that we can get to our final dimension, but I'm going to do it like 1,000th at a time because it's the whole cutter. And that was it. So now, as long as I'm here, I'll probably take the same 1/8 inch end mill and go back and clean up V, and then I have to flip this thing 90 so I can get a square on this other side here, because this radius might be a little bit too much. It's like a couple thousandths too much, so we're going to flip this part after I'm done. So I would have been better off if I'd used a 1/4 inch end mill to clear all this excess material out of here. Would have been much, much faster, but you know, I didn't, so I learned some things and I'll do better next time. Alright, so now I've just taken the part like this and flipped it like this, the other 45, so I can get square corner on the other part. So that's where I'm headed. You won't be able to see that from this camera angle, so I'll just bring you back when I'm done. Alrighty, so this part's done. There was a foop right as I got to the end here, actually two of them. There was only supposed to be a hole on one side, and I got a hole on the other side as well that's drilled and tapped. The end mill in the end mill holder, the 1/8 inch end mill, popped loose at the end of the milling operation and ginked up the part. So I told the customer about it, and the customer is in a hurry for the parts. So he would rather have the parts now, since that doesn't affect functionality, rather than wait for it. And so I'm going to ship him the part, but I will not charge him for it because I don't ship parts that aren't to spec according to the drawing. So he'll get this part for free, and I hope it works out for him anyways. Because besides this, the end mill popped loose here, and I didn't even notice, and it actually in-cut a little bit on this shelf. And then as I brought it out, that's when it really got loose. It just started to get a little loose here and then big time loose here. And anyways, very frustrating because it was right at the end of the part of the milling operation with the 1/8 inch end mill, which was really painful and slow. So I offered to make the part, like I said, but the customer's in more of a hurry than wanting the perfect part. So he said this will still work for him, so it's free. All right, moving on. This last part is going to be a tough one. Here's the part here, here's the piece of material, and it's going to be challenging because you've got compound angles on drilled holes, and so we're really going to have to work this one carefully. I estimated 2 hours for it. That's funny because it's going to take a lot more, I believe. But in any case, it's going to be a definite learning experience. And actually, the customer, normally I try to enter in CAD, but I'm not good with 3D CAD. And I'm just learning Fusion, but not there yet, definitely. So the customer provided me some 3D sketches reference to a tooling ball. So let me go grab that here. We will be using this tooling ball for a reference point. So I will be drilling an extra 1/8 inch diameter hole that I'll be drilling and reaming that will fit this tooling ball. Now this tooling ball has some useful features. This is one with a shoulder. They sell them without the shoulder, without this little piece on the bottom. The ones with a shoulder guarantee that when the part sits flush against the shoulder, the center of the ball will be a known distance from the base, which in this case is 200 thousandths. The other advantage with a tooling ball in general, minus the shoulder or with or without the shoulder, is that this is a 1/4 inch ball, and so you know that wherever you touch the ball, you are 0.125 inches, half the diameter, from the center point of the ball, and that will give me a location, a reference point to work off of when I rotate these parts on a sine bar. So it's going to be an interesting setup here. But before we do that, we've got some slots to drill, and we also have some holes and countersinks to drill. So we're going to do those first, and then we'll get on to the really hard part. One more thing, I would have left these holes till last because they're really easy to do because they're all referenced off of square surfaces in a normal orientation. But I actually need these to mount to a plate because I need something to hold this down to the sine bar. So I'm going to screw this to a plate that'll be held to the sine bar so that I've got access to this part. I also have to do the slot here. First up, we're going to drill and countersink these holes here, these 4. 1, 2, 3, 4. Next up, I'm using a counter bore, and they want a specific depth, so I'm using gauge stock to hold this down here, set my 0, then compensate for the 21 thousandths, and we are looking for a depth of 170 thousandths. Gotta slow it down though. One down, 3 go. Oh, yeah, that's a perfect fit. All right, so there we go. There's my tooling ball reference for when we go to drill the 2 holes here. And I'll remove the tooling ball each time before I do it, but fits in there nicely. Alrighty, so drilled and tapped. I have a fixture plate, and I purposely biased it towards the top because my sine bar that I'm going to use is pretty tall, and I thought I could have plenty of room to clamp down here, but we'll see. It doesn't need to be centered, and so 832 cap screws. Now one more thing I'm going to do is I've got to flip this guy upside down, and I've got to machine out the center 6/10 of an inch. So we're going to do that, and then we have just 2 holes to drill. Alright, last stop before the compound angles. We need to remove a slot 6/10 wide. This is a 1/2 inch diameter cutter, so 6/10 wide, plus or minus. So we'll take this down to 4/10 of an inch. We will take this guy down to almost final depth, and then we'll go plus or minus 50, and that will give us our 600 thousandths. By the way, in case you didn't notice, I've been going counterclockwise all the way around, and that gives me climb cut all the way around. All right, so the gap between here is definitely not a precision part, but if it was, one way to measure it fairly accurately would be to take a adjustable parallel, slide it in, make sure you're not caught on a burr, and then measure across the adjustable parallel. Right on the money. It's supposed to be 0.6. How about half a thousandth over? So even though we weren't trying to be super precise, we pulled it off anyway. Alrighty, so here's the part mounted on the fixture plate. I've got the screws somewhat loose still because I have to first indicate on this side, then indicate on this, and make sure that these guys are square to each other, and then cinch it down. Maybe I'll do that in the vise. Alright, so I double checked that my vise is trammed in, and it sure is. So I've got just this rear screw tightened here, and what we're going to do is we're going to walk in on one side of the part here and go. I know you can't see the indicator because it's aimed at me. It's going up, so we need to gently tap. Wrong way, sorry about that. Yeah, needle's not even moving. Okay, so now what that allows me to do is indicate off the edge of this, or make the edge of this square to the side of the sign bar, and I know that I'll be in good shape. Alright, so the first hole we're going to drill is the easiest one, and it's just at an angle 35.5 degrees on the center line of the part. So I'm going to use my edge finder here. Let me give you some light. I'm going to use my edge finder, and I'm going to go find this side, go dead center. And it should be right on that center line. Then I'm going to use my edge finder to find the edge of the ball right here. And the customer, fortunately, has provided the ball in space. The center point of the ball is equidistant from all sides of the ball. And so he gives me the distance from the center point of the ball above the ball to where the hole should be. So I will get my quill right over that spot, and we should be good to go. So let me do some measuring. And oh, by the way, this is a sign bar, and it's a 5-inch center, so that's the hypotenuse. So sine of the angle right here, 35.5, this angle right here is opposite over hypotenuse, is the unknown height of the gauge block stack over 5, or 5 times sine of 35.5 is equal to the unknown stack size. And when I plug that in my calculator, 2.9035 inches, and I have that exactly in there, including the tenths. So we're going to try and be as accurate as possible. Alright, so I've gone side to side with my DRO, found the center point, which is where I'm at right now, and I'm going to lock that off. Of course, it always shifts on me. Alright, so we've got the ball here, and we're going to come down, and we're going to touch off on the ball and set my 0. And so now we are 0.125 from the center, but at 100 thousandths for the thickness of the half the diameter of the edge finder. So 0.225 in will be my 0, and I'll set my 0. That should be right over it. And then if I go to the other side, okay, I get 0.225 on the other side as well. So we are good. Just to verify, I'd like to do an idiot check. So now we take this out, and we can drill. So we know that the hole is on the center line, and it's 0.4345 north of the hole. All right, so first step is we're going to come in with a 1/8 inch end mill to get a flat spot to bear on. Then I'm going to try and follow that with a center drill, then an undersized drill bit, and finally a reamer. And we're going to go very easy. Okay, so we were able to go all the way through with the end mill, so I won't need the center drill. We will follow with a drill bit. This is a center cutting end mill. So we're going to try and hopefully get this thing to drill straight. Okay, hopefully that went straight. One hole down. Let's fixture up the next one. This is the one with the compound angle, a little bit more challenging. All right, next up is the compound angle. So we've got the sign plate here set for, let's see, what is this one? This is 37.9 degrees. And we have the second sign plate here set for 18.9 degrees. And it wouldn't fit on the base here, so I had to use a parallel to put it on, and then I clamped it in place so I could actually remove that sign bar because the part's held in place, but I'm going to leave it there for now. Now for this one, I need to do X and Y off of the ball because I can't go off the edges anymore. All right, after a lot of effort, I have got my indicator set so I can find my zero in the X direction, which is this way. Which is the hardest. The Y direction was pretty easy because the side of the ball is exposed, but the uphill side of the X side, this edge finder is 200 thousandths wide, and it just barely fits down low enough because, you know, I'm measuring a point up here on one side and then sort of towards the bottom of the other side of the ball, and I got to get it down there. And I always do a sanity check, so I make sure that when I go from one side to the other side, that's exactly the same, and it is. So we are there, and we are good. So next up, we just do our offsets, and then we drill. Alrighty, so now I'm done with the tooling ball. Now that I've got my zero in that imaginary point in space, so now I just dial in my offsets. So we'll start with the X, the Y offset this way, and it should be 0.1552, and the X offset is 0.4059. And we have a sign bar down here to rotate the part 18.9 degrees, and another, get this angle, 37.9 degrees, another sign bar here, 37.9 degrees, holding the part in place to drill through. And again, we use the tooling ball in the center hole to find my zero, and then I got my offsets from the customer, and we're going to drill the hole. And again, we are going to drill with an end mill first. And we're done. All right, so here is the part finished. This was a really tough one to set up, and my confusion was I thought this was the center line, and so I thought this was the center line, and I thought that made the part left, but I was misreading it because the center line's here, and I needed to drill to the right of it, which I ultimately did. So there it is, and the other parts for this project are this one, which I screwed up and I will not be charging the customer for, and some boring ones like this base plate that I think this guy mounts on somehow. Not entirely sure, and 2 plastic parts. And we're done, so I'll be shipping these out. Another challenging project from this customer. He comes up with some really creative parts he wants made, so I like the challenge, and he's really nice to work with. So thanks for watching. Hope you find it useful. Hope to see you next time.